Now we are moving into the concept called Doob's Martingale process. When we say the given stochastic process is going to be a Doob's Martingale process or Doob's process. See the definition. Let yn be a arbitrary sequence of random variables, and suppose x is a random variable with expectation in absolute finite. Define xn is the conditional expectation of xn given y0, y1 and so on till yn for every xn, where n is running from 0, 1, 2 and so on. Expectation of x given fn plus 1 given fn. We know that fn is contained in fn plus 1, and using the property this becomes expectation of x given fn, that is same as x suffix n. In essence, as n increases, xn approximates x, and the approximation becomes more refined because more information has been gathered and included in the conditioning. Thus, xn, n is equal to 0, 1 and so on forms a martingale with respect to y suffix n, where yn is equal to 0, yn for n is equal to 0, 1, 2, called the Doob's process. Now we define submartingale and supermartingale. Submartingale and supermartingale by replacing the equality in the equation 1, the equation 1 in the definition of martingale, whether it is a discrete time or the continuous time. If you replace the equality sign with a greater than or equal to or less than or equal to respectively for any 0 less than or equal to s, less than t, less than or equal to capital T, the third condition, the first two conditions are expectation exists, and then xt is ft measurable or xn is fn measurable. That's the two conditions. So there is no change in those two conditions, only the change in the third condition, that is by replacing the inequality in equation 1 of with greater than or equal to, less than or equal to, then the corresponding stochastic process will be call it as submartingale whenever it is greater than or equal to sign, or it is supermartingale if a conditional expectation is less than or equal to x of s. If it is equal to for all this interval, in that case it is a martingale. If this property is satisfied greater than or equal to s, where s is less than t and t is less than or equal to capital T, then the stochastic process is called a submartingale, and the less than or equal to condition is satisfied, then the stochastic process is called a submartingale. Now we present the Poisson process is a submartingale. We take the same example. N of t is a Poisson process with the intensity lambda, and earlier we have proved n of t is not a martingale because a conditional expectation is greater than or equal to n of s, because t minus s is greater than 0, lambda is strictly greater than 0. Therefore, this quantity is greater than or equal to n of s. Hence, conditional expectation of n of t given f of s is greater than or equal to n of s. It's always greater than or equal to for all s less than t, where t is less than or equal to infinity. So this condition is satisfied for all s and t. Hence, the given stochastic process that is the Poisson process, is a submartingale because of this greater or equal to sign. Now we present the Wt square is a submartingale where Wt is a Brownian motion. Wt is a Brownian motion, so we are going to use the property of Brownian motion. That is a one particular important stochastic process which has a lot of applications in financial mathematics. So here we are going to prove Wt whole square is a submartingale. How? The conditional expectation of a Wt whole square given f of s is you add one term and subtract one term, that is plus ws minus ws inside the Wt whole square. Using the identity, Wt minus ws plus ws whole square will be same as Wt minus ws whole square plus 2 times ws Wt minus ws plus ws whole square. So why I am doing this way of adjustment? Because I am going to use the property of non-overlapping intervals are independent. We are directly checking the conditional expectation. The first two conditions are obviously satisfied. The first one is Wt is integrable. The Brownian motion, for fixed w, for fixed t, Wt is normally distributed with the mean 0 and the variance t for a standard Brownian motion. Therefore, the mean exists. The second one, Wt is Ft measurable. So whenever we didn't discuss the filtration, that means we have a natural filtration f of t. Whenever we have a natural filtration, that means this random variable is Ft measurable. F of W of t is Ft measurable. Therefore, second condition is also satisfied, and we are checking the third condition. The third condition, the right hand side, Wt minus Ws whole square plus 2 times Ws times Ws minus Ws plus so on. So now we are applying the conditional expectation here given f of s. Therefore, the conditional expectation is a linear operator. Therefore, it is a conditional expectation of this term given f of s, conditional expectation of this term given f of s plus conditional expectation of this term given f of s. You know that f of s is nothing but the information up to time s. And Wt minus Ws, that is also normally distributed with the mean 0 and the variance t minus s. I am discussing about the standard normal distribution. Later we are going to discuss the Brownian motion in detail. So here I am going to use only the distribution and the mean of a Brownian motion as well as a independent property. So here the Wt minus Ws is independent of f of s. Therefore, the conditional expectation is nothing but expectation of the Wt minus Ws whole square. Since Wt minus Ws is normally distributed with the mean 0 and the variance t minus s, this this expectation is nothing but the t minus s. The second term, again 2 times conditional expectation of Ws multiplied by Wt minus Ws given f of s, and the f of s is independent of Wt minus Ws, and you have the information till s, therefore Ws has to be treated as a constant. So the 2 times Ws will be treated as a constant. So hence expectation of Wt minus Ws given f of s is nothing but expectation of Wt minus Ws because of f of s is independent of Wt minus Ws, and you know that expectation of Wt minus Ws is 0 because this is normally distributed with the mean 0, variance t minus s. The third term, the conditional expectation of Ws whole square divided by f of s is nothing but ws whole square, because you know the information till time yes, therefore ws whole square has to be treated as a constant. Expectation of constant is constant. Hence, expectation of wt whole square given f of s is nothing but t minus s plus 0. So, hence t minus s plus ws whole square. So, this is obviously greater than or equal to ws whole square. Therefore, the wt whole square is a submodule because it satisfies the third condition with the greater than or equal to sign in the conditional expectation. Therefore, the stochastic process wt whole square is a submodule. Some remarks: a stochastic process, let's say of random variable xn, is a submartingale with respect to the filtration fn, n varies from 1, 2 and so on, if and only if minus xn is a supermartingale with respect to the same filtration f. The if and only if is very important. Whenever you have a submartingale, you can always convert it into the supermartingale with the minus sign. Or if you have a supermartingale, you have a stochastic process with the supermartingale property satisfied, then you can convert this stochastic process into the submartingale stochastic process by changing the sign. Note that both the stochastic process, we are discussing the martingale property, submartingale or supermartingale property with respect to the same filtration. That is important. You cannot convert submartingale into supermartingale with a different filtration. Not in general. If you have a same filtration, then you can transform the submartingale into supermartingale by changing the sign in both ways. The second remark, a stochastic process xn, n varies from 1, 2 and so on, is a martingale with respect to the filtration fn if and only if and only if xn is both submartingale and the supermartingale with respect to the same filtration. That means if you have a given stochastic process of martingale, if and only if the same random variable will be treated as a submartingale as well as supermartingale, because we are replacing the equality sign by greater than or equal to. Similarly, less than or equal to. We are not replacing by strictly greater than or strictly less than. Since we have replacing the equality sign in the conditional expectation of the third condition in the definition of martingale with less than or equal to, greater than or equal to. Hence, if you have a martingale, then the same thing will be supermartingale as well as submartingale. Similarly, if you have a stochastic process is both submartingale and supermartingale without changing the sign or without doing any change, the same stochastic process is a submartingale as well as a supermartingale, then definitely that will be a martingale. Because if it is both submartingale and supermartingale, that means there is no the conditional expectation with greater than or equal to or less than or equal to. It must be equal to the conditional expectation. Hence, the given stochastic process is a martingale. These above remarks is also valid for continuous time. In this lecture, we have covered the definition of martingale in continuous time, the definition of martingale in the discrete time. Then we have discussed a few examples. and followed by that we have discussed when we can say the given stochastic process is a supermartingale or submartingale. We have given few examples for the supermartingale as well as submartingale also. And finally, we have given some remarks over martingales, submartingale, and supermartingales. Here is the list of references. With this, the lecture 2 of module 6 is complete.